Hi, thank you very much for attending my session. So, for the next 1 hour, I'm going to talk to you about what you always wanted to know about deep learning but were afraid to ask. My name is Wei Meng, and I am the technologist and founder of Developer Learning Solutions. So, let's get started. Agenda for this session. So, first thing first, I want to talk about what is deep learning. I'm sure you have heard of this term called deep learning. So, hopefully, this session would demystify this concept around deep learning. What exactly is deep learning? Now, when we talk about deep learning, we want to talk about neural network. So, in this session, I will explain to you how a neural network works. And when you talk about neural network, you have to talk about weights and biases. You will understand what are the uses of the weight and biases in a neural network, and how you can actually use activation and loss functions to actually optimize or rather to minimize the loss of a neural network, and how you can use optimizers and this technique known as back propagation to actually improve on your deep learning model. So that is for the theoretical part. For the demo part, we are going to build neural networks. I'm going to show you demos of neural networks using the TensorFlow framework as well as the Keras API. And so in particular, you will learn how to use the MNIST dataset for deep learning, how to recognize handwritings, and you will also learn how to train using your own images, and you will build a model to learn how to recognize fruits like oranges, uh, bananas, durians, and strawberries. So we will also show you, I will also show you how to export TensorFlow models to TensorFlow Lite so that your model that you have already built can run on mobile applications. So all in all, for the next 1 hour or so, there will be about 60% theory and 40% demos. So let's move on. So is this session for you? So if you are already an expert in deep learning, then probably this session is too simple for you. You can go and have your beer. If not, enjoy the rest of this session. Now, it is important for me to clarify that deep learning is a huge topic, and it usually takes a semester-long course to cover just the fundamentals. But I'm trying to attempt the impossible. I'm trying to make it as simple to understand as possible, and I'm going to cover it in 30 minutes. So hopefully you will stay with me, and then at the end of the session, I hope you have a good understanding, or at least a conceptual understanding of what is deep learning. So this session is going to focus more on the how and not the why. All right. Now, you always see three terms, AI, machine learning, and deep learning used interchangeably. So let's take a look at what is the difference between these three terms and how you can actually differentiate between them. Now, first of all, in the broadest definition is AI, artificial intelligence. AI refers to programs that can sense, reason, and adapt. So as long as a program can reason very much like a human being, it can be classified as AI. Now, within AI itself, you have this field known as machine learning. So what is machine learning? Machine learning is basically finding patterns in data. So most of you would be familiar with this concept in one way or another. For example, if you have taken a course in statistics, you would have learned something called linear regression, where you plot a series of points on a chart and you try to draw a straight line that fits through most points. Now, using this line, you could actually make some predictions. Okay, so that is linear regression, and linear regression is part of machine learning. Now, within machine itself, there is another field, which is the main topic for this talk, and that is deep learning. So deep learning is a multi-layered neural networks that can learn from vast amount of data. And we're going to take a deeper look into deep learning in the next 1 hour or so. Now, a common question that people always ask is that AI, are we there yet? So the answer is that if it works, it's not AI. So obviously we are still not there yet. We are still some time away from having a really intelligent AI applications, but we are making good progress. Now, so what is deep learning? So what is deep learning? Now, generally speaking, deep learning is a machine learning method that takes an input X and predicts an output Y. Okay, so you pass in a set of inputs and the associated output for this set of inputs. And what deep learning will do is that it tries to find the association. It tries to learn the association between the inputs and the output. So this is represented by this figure here. You take a set of inputs as well as the outputs, and deep learning will magically try to learn the relationships between the input and the output. Now, how does this magic work? And this is the focus of this talk. So, when we talk about deep learning, we need to talk about neural networks. So let's take a look at a sample neural network. Now, so what I have here is a very simple neural network. So on the left hand side is your set of inputs, and each circle here represents a node, or in deep learning terminology, we call this a neuron. So I have on the left the input layer, where I have all the nodes for input, and I have the output layer. And in between this output and input layers, I have the neural layers. And each neural layer contains a number of nodes or neurons. And each of these nodes are interconnected. All right, we will talk about the relationships between all these nodes shortly. Now, so this is one example of input and output. So if you want to develop a deep learning model to be able to differentiate between a dog and a cat, so your inputs would be a series of pictures or photographs of cats and dogs. And your output would be the label for the picture, a dog or a cat. So in a neural network, what you are trying to do here is that you are trying to pass in a set of images representing cats and dogs with their associated output, and you want to be able to establish a set of rules or relationships between the input and the output. And that is the role of a neural network. Now, let's talk about some terminologies. Now, between the input layer and the output layer is your hidden layer. We call it the hidden layer. So in a typical neural network, you can have one or more hidden layers, depending on the complexity of your neural network. Now, the next important topic that you need to understand is what we call weights and biases. So let's take a look at them. Now, if you recall our neural network that I have shown you some slides ago, you have your input layer, you have your output layer, and you have all the various neurons in the hidden layers. Now, each node, as you have seen earlier, is connected to the next node. And in this case, we call this a fully connected neural network. So each connection here has got a number known as a weight. So as you can see from here, x1 connect to this particular node, I have a weight of 0.2, and for x1 to the next node, I have a weight of 0.1, so on and so forth. And on each neuron, I also have a number known as a bias. And so in this case, I have a set of biases. Now, initially, before you actually train your neural network, all the weights and biases, they are randomly assigned. So meaning, before you start, you randomly assign some numbers to the weights and biases. So the main goal of training a neural network is that at the end of the training, all the weights and biases would automatically be adjusted so that it can best represent the relationships between the input and the output. That's all training is all about. So the goal of a neural network is to learn the weights of the network so that the predicted output is close to the target. Right? So that's the goal of a neural network. So using the example that we have illustrated earlier on, so what we want to do here is that we try to magically find the set of weights and biases that can best represent or map the input of a photo of a dog to the output, which is the dog label. So that's what we are trying to do. Now, how does the weights and biases work in a neural network training? So this is how it works. Now, if you look at the input here, x1, x1 is connected to this neuron. It has got a weight called w1, and this neuron here has got a bias called b. So this is what happens. So you take the input x1 multiplied by the weight 1, and you add it up with the next product, which of x2, w2. You add it to the next product, x3 multiplied by w3. You sum them up plus the bias. So that's how you derive the value for this particular neuron. Now, so here is one example. So in this example for node 1, I take the age, which is 18, multiplied by 0.2, add it up to 2 multiplied by 0.12, add it to 1 multiplied by 0.1, plus the bias for this node, and I get a value 4.74. So likewise, I do the rest of the calculation using this method, so I can calculate the value for this node, for this node. Okay, so this is what happens at this layer. Now, the next important topic that you need to understand is activation function, right? So what is an activation function? So an activation function basically maps the value of a node to another value. So if you look at the previous computation that we did, we sum up the product of wi and xi plus the bias. And so what we do here is that we take the value here that we have computed, feed it into an activation function, and the activation function will return you a brand new number. So that is the use of an activation function in a neural network. Now, so let's take a look at this example. Using the previous example, after computing the product of all these connections and adding the bias, which we got 4.74, we are now trying to take this value and feed it into an activation function. And for this example, it returns you a value of 0.84. Now, don't worry too much about why we get 0.84. I'm going to show you the various types of activation functions that you can apply to a neural network. Now, so what happens here is the use of an activation function allows you to control or normalize the output of a neural network. So after you have computed the value at a particular neuron, you pass it into an activation function. It transforms that number from one number to another number, and you take the number and you continue the same process. You multiply, you sum them up, you add the bias, so on and so forth. Now, so that is the use of the activation function. Now, at this point, activation function may seem a little bit abstract to understand, okay? But an easy way to understand an activation function is to consider the use of an activation function at the end of the neural network, which is the output layer. So for example, if you are trying to solve a classification problem where the outcome must be either a 0 or a 1. So when you calculate all the numbers and towards the end, so instead of having a big number like 5.2, 5.9 or 0.25, you want to be able to restrict the value to a certain specific range. And in a classification problem, for example, you want to limit the output to be a 0 or 1. So the use of the activation function would allow you to take a number so that once you feed it in, you can get back a number from 0 to 1. So that's the use of an activation function. Okay, so over the next few slides, I'm going to show you some other types of activation functions that you can use and what are the commonly used activation functions in deep learning. So let's talk about the different types of activation functions. So broadly speaking, there are three main types of activation functions: binary step activation function, linear activation functions, as well as non-linear activation functions. So let's go through each one of them in more details. So the first one is called a binary step function. So binary step function is pretty straightforward. So you check the value. So whatever value that you pass into this binary step function, if the value is a positive number, it returns you a 1. If this input is a negative value, it returns you a 0. So that is a binary step function. Now, besides a binary step function, you have a linear activation function. Now, linear activation function looks very much like a straight line. So whatever value that you input, you multiply by a constant, you get an output. Now, a neural network with a linear activation function is not really that useful. So it basically, if you have a neural network with linear activation function, it simply transforms that into a linear regression model. So for that reason, linear activation function is not often used in a neural network. So we're not going to focus too much time on that. Now, what is more important is your non-linear activation functions. So an example of a non-linear activation function is known as a sigmoid activation function. So if you look at this chart here, so if your input is more than 0, then your output would be transformed into a value between 0.5 and 1. And if your input is a negative value, then your output would be transformed into a number between 0 and 0.5. So a sigmoid activation function is very useful for predicting probabilities. So for example, in your neural network, if you're trying to predict a probability of something happening, so at the output layer, what you want to get is a number between 0 and 1 that represents the probability of something happening. So in this case, a sigmoid function would be very useful that you can use at the output layer to constrain the output between 0 and 1. So for example, you want to predict the probability of survivor in the Titanic incident. So you can predict, let's say, the survivor probability of a person of a particular demography is 0.93, for example. So, like I mentioned, the sigmoid activation function is very useful at the output layer where you have, let's say, one node. You just want to predict a probability. Now, another type of non-linear activation function that you will come across very often is called the Softmax Activation function. So Softmax Activation function is very useful for probability distribution output, where you are trying to detect the existence of various objects, for example. So, for example, you have a neural network that is trying to predict, okay, at the end, what is the probability that this image contains a dog? What is the probability that this image contains a cat? And what is the probability that this image contains a guinea pig? So, the sum of these three probabilities must be equal to 1. So using the softmax activation function, you can actually input the values that you have, and it would generate a list of probabilities that sums up to 1. So that is the use of a softmax activation function. So here is the summary. So it is very often used when you have a few neurons at the output layer, and all the values must sum up to 1. Now, there are some more non-linear activation functions that you sometimes use in your deep learning model. Another one is known as the hyperbolic tangent activation function. So it is also used mainly for two-class classifications. If you look at this chart here, the difference between the hyperbolic tangent activation function and the sigmoid activation function is that if you look at a sigmoid activation function, the output ranges from 0 to 1. whereas the hyperbolic tangent function, the output ranges from +1 to -1, so it has got a wider range. Now, another very commonly used activation function, in fact, the most commonly used activation function in use today is known as the ReLU, or Rectified Linear Unit Activation Function. So if you look at this chart here, so for a sigmoid function, the value can range from 0 to 1. Same goes for the ReLU. But if you look at the ReLU, as long as the value is more than 0, it will return you a linear function. But if the value, the input to this activation function is less than 0, it would straight away give you a flat 0. Unlike the sigmoid activation function, where if your input is less than 0, it will still return you a value from 0 to 0.5. Now, there are some problems with the ReLU activation function, because anything that is less than 0, it would flat off return you a 0. Sometimes that is not ideal. So in order to solve this dying ReLU problem, researchers have came up with another modified ReLU activation function called the leaky ReLU. So as you can see from this chart, if the input is less than 0, instead of returning you a flat 0, it returns you a small little value multiplied by a small gradient, so that you don't flat out get a 0. Okay, so that is known as leaky ReLU. So in summary, based on what we have discussed so far, you learn that for each connection there is a weight, and for each neuron there is a bias, and the use of the weights and bias is to basically multiply them, add them, and then move on to the next layer. And on each layer, you feed the product and the sum to an activation function so that you can derive a new value, and a new value would be used in the next level of calculation. So you use the activation function at all the different layers, or the hidden layers as well as the output layers. And in particular, at the output layer, if you are trying to calculate a series of probabilities that sums up to 1, you can use the Softmax Activation function. Whereas if you are trying to, in your output layer, you only have one node, one neuron, and so in this case, you can use the Sigmoid Activation function. So this is some of the uses of the activation functions. And in the hidden layer, at this moment, the most commonly used activation function is known as the ReLU activation function. Next thing, loss functions. After the neural network has passed all its inputs all the way to the output, after you multiply all the numbers, you pass it into activation function, get a new number, and then multiply, sum again, put it into activation function, repeat until the end. The neural network must have some criteria to measure how well did the calculation go. Okay, how far are you away from the expected output? So this is called a loss function. Now, if you are trying to solve a regression problem, you can use a loss function called the mean squared error loss function. So the goal is to minimize the loss function. So in this case, you take the expected output, you minus the predicted output that you have calculated, you square them, sum up all the values, and divide it by the total number of samples. And you want to minimize the loss function. So if you get a value that is really small as 0, that means that your prediction is very close to the expected output. So that's good. Okay, so that is called a loss function. Now, so to sum up, a loss function is basically a summation of the errors made for each example in training or validation sets. So it shows how well the model is doing for these two sets. And unlike accuracy, loss is not a percentage. So the lower the loss, the better a model. So depending on the type of problems that you are trying to solve, if you are trying to solve a binary classification problem, you can use this loss function called binary cross entropy. If you are trying to solve a multi-class classification problem, then you can use the loss function called categorical cross entropy. And like I mentioned earlier, if you are trying to solve a regression problem, then the model outputs a predicted value, and in this case you can use the mean squared error function. So what is the meaning of cross entropy? So let me just give you a very simple explanation. So this chart here shows the loss value when the true label is 1. So basically it means that, hey, if the true value is 1, you're trying to hit a value of 1, and if your prediction, if after the calculation your prediction is 0.9, so if you look at this value, if your predicted value is 0.9, for example, you are somewhere here, then your loss value would be very, very small. But if the true label is 1 and you predicted something to be 0.1, so if you look at this chart here, then your loss value is very, very high. So in this algorithm, for cross entropy, you would be penalized if your prediction is very well away from the target output. So if I get 0.9, my loss value is very small. But if I get 0.1, then my loss value is very, very high. If my prediction is 0, then you can see that my loss value is extremely high. So it penalizes you if you make a prediction that is very, very far away from the target output. Okay, so that is the idea behind cross entropy. Now, so after talking about all this technique, so you use activation function at every layer so that the values can propagate to the next level, and you use a loss function towards the end to measure, after doing all the calculation, how far are you away from the target output. And using this loss function, you can now use an optimizer so that you can now go back to the neural network and update the weights and biases one by one, so that in the next round of calculation, you would further reduce your loss function. And ideally, after many passes, you would be able to have a set of weights and biases that allows you to actually get a very small value for your loss function. So that's the aim that we are trying to hit. So what are optimizers? So optimizers are basically algorithms that allows you to go back and update your weights and biases. So there are few commonly used optimizers that we use in deep learning. So the first is called a stochastic gradient descent, or SGD, and the second one is called an ADAGRAD, and the third one is called ADAM. Now, we will not be going into the details of how all these algorithms work, but if you are interested, later on I will show you a link that allows you to explore all these algorithms in more details. So, optimizers uses a technique known as back propagation, where you go back the various layers in the neural network, update the weights and biases, so that you can actually improve the performance of your loss function. So using the back propagation technique, you would be able to take a look at the output and then go back, update the weights and biases, and this technique is known as back propagation. Now, using back propagation, the network backtracks all its layers to update the weights and biases of every node in the opposite direction of the loss function, and every iteration of backpropagation should result in a smaller loss function than before. And this continuous updates of the weights and biases of the network ultimately turns it into a very precise approximator, so that you will be able, at the end of the training, you will be able to enter something brand new, and it will be able to help you accurately predict the output. So that is the use of backpropagation. Now, at this point, it is good to summarize what we have covered so far. We have activation functions used at every level, every layer, and then at the output layer, we use the optimizer. We use the loss function to calculate the loss value, and using the loss value, we would use the optimizer to perform a back propagation so that we can go back and update our weights and biases. And this goes on and on and on for many, many iterations until we find an accuracy that is good enough for us to stop our training, so that we can actually use this to actually predict our brand new data. Okay, so far up to this point, this is the theory part that we want to talk about. I think it is important, it's useful for us to see some demos so that we can put this into perspective. Let's take a look at some demos. Okay, so for the demos, we are going to make use of this framework known as the TensorFlow and Keras. So TensorFlow is an open source library for numerical computation and deep learning. The problem with TensorFlow is that it is not so easy to use. You have to go to very low level TensorFlow objects to actually build your deep learning model. So to make things easier, you will make use of this Keras. So Keras is a TensorFlow's high-level API that allows you to build and train deep learning models easily without really going into the very low-level details. So I'm going to show you a few demos. So the first demo that I'm going to show you is basically building a artificial neural network using the MNIST dataset. So the MNIST dataset is basically a collection of handwritings containing the digits from 0 to 9, and with a label to label whether this image represents a 0, 1, or 2, or up to 9. So what we want to do here is that we want to build a deep learning model making use of this dataset, and then we can actually use some hand-drawn images to feed into this neural network to actually help us predict whether this handwriting contains which digit, 0 or 1 or 2 or up to 9. So that is the use of this first demo. I'm going to show you to you shortly. Now, the second demo that we will show you is using what we call a pre-trained CNN model. So CNN stands for Convolutional Neural Network. So it's a special type of neural network that is designed for image recognition. So, and in particular, we will make use of this technique known as transfer learning to recognize our set of fruits: bananas, durians, strawberries, and oranges. So, transfer learning basically means you take a model that has already been trained by some other fellow developers. You take the model from them, and because a model contains many different layers, in transfer learning, you strip away the last few layers and append the last few layers with your own layers. So the idea behind transfer learning is this. The model that has already been trained, it is very good at recognizing certain objects, certain images. And the first few layers that you are going to maintain is good at recognizing certain outlines of images, some certain objects. And the last few layers that you're stripping away and you're adding your own layer is to basically get that model to recognize very specific objects. And in this case, we are adding the last few layers to our neural network so that it can help us recognize images like bananas, durians, strawberries, oranges, depending on what you are trying to train to recognize. So this demo also shows you that after you have performed the training, you can actually save the model so that it can be loaded at a later time, so that you don't have to incur the time training again. So that's the second demo. Now the third demo allows you to actually activate your webcam so that you can actually make use of the model that you have trained in the previous demo to recognize images through your webcam. So I'm going to show you how to actually take an image, put it in front of the webcam so that it can recognize what kind of fruit it is. So that's the third demo that I'm going to show you. The fourth demo, it's basically involving the first demo. So in the first demo, you are able to write, to recognize handwritings. So after training the model to recognize handwriting, I thought it would be fun to be able to take the model that you have trained and put it onto a mobile application. So what I've done here is that I have taken the model that I have trained in the first demo, converted it into a TensorFlow-like model, which is suitable for use on your mobile application. And I have used Flutter to build a cross-platform app so that I can write an application that runs on both iPhones and Android devices. And I am going to allow the user to scribble onto that device. So, excuse me. So that whatever you have, the user has scribbled, it is able to recognize what digit it is. Okay, so I'm going to show you that demo shortly. And the last demo is this. I'm going to show you how you can actually make use of a pre-trained model by Google to recognize different objects in an image. So again, I have built this application using Flutter, and it uses TensorFlow Lite. And this application, when you load it up with photographs of your on your phone, it is able to tell you with some pretty good level of confidence what are the objects that it has detected in your photograph. So this is again very cool. So I'm going to show you a demo very quickly. Okay, so the first demo that we want to demonstrate is the one on the MNIST dataset. So first thing first, I am going to import all my necessary modules and libraries. And next thing, I want to load up my dataset. I'm using Python, so I want to load up my dataset. So let's load up the dataset. And so let's print out the sample so that we can take a look. And I want to print out the dataset graphically so that I can see the images. So I'm going to run it. So as you can see, it is basically images 28 by 28 pixels, and it has got basically scribblings of the digits from 0 to 9. And I just want to print out the shape. So I have 60,000 of them that I can use for training, and I have 10,000 that I'm going to use for my testing. So, and because they are in color format, I want to convert them to grayscale. So I want to divide by 255. So all the values are now from 0 to 1. And I have 10 classes because I have digits from 0 to 9. So altogether there are 10 classes. And I want to build my model. Now this is where you start to build your model. And I am using the sequential model. And I am trying to specify how many input-output layers I have, what is the activation function that I want to use. So in this case, I use ReLU, and at the last output layer, I want to use a Softmax. Remember, I mentioned that if your output has got multiple neurons, and in this case, I have 10 neurons because I want to separate them into 10 groups, 0 to 9. So in this case, I want to use the Softmax activation function, so that each neuron, each output would contain a probability from 0 to 1, and the sum of these 10 probabilities must be equal to 1. So let's build our model. So my model is now built. And next, I want to compile my model. So, and because this is a multi-class classification problem, so I use a categorical cross entropy loss function, and I want to use this optimizer Adam so that I can use this algorithm to do back propagation to update my weights and biases. And the metrics that I want to use to measure is the accuracy. So I'm going to compile this model. So done. Now, this part here basically allows you to start training the model. Okay, so I want to train the model, and so let's see how it works. So it is now training. So there are a number of iterations that you want to keep on repeating, and this is known as the epoch. So in this case, I want to train it 50 times. So for each time, it prints out the accuracy. So you can see that the accuracy is getting better and better. So let's wait a second for it to finish. Now, the training time usually depends on the complexity of your model, as well as the total number of items that you have for training. So for simple model, it takes a couple of minutes, and it is not unusual for you to take days and weeks to train a complex model. So let's look at the output. So now we are near 41. So okay, not too bad. Okay, I think we are finishing. There you go. So the final accuracy that we get, it's about 0.97, which is pretty good. So we want to evaluate that with the test set. So, and we have achieved a test accuracy of 0.97. And we can plot the chart for the various metrics, accuracy, as well as the loss function. And let's pull out a sample image from the test set to see how good our predictions are. So let's run this. And so in this case, it predicted that this is a 9. Okay, so it's pretty good. And it shows you the probability for each group from 0 to 9. So as you can see here, which is the one that has got the highest probability? The last one. Okay, so this is it has correctly predicted that this is a digit 9 from 0 to 9. So this is the one with the highest probability if you compare that with the rest. Okay, now and the rest allows you to actually do the prediction. Now I can also save my model as a H5 file, so I can save it. The nice things about saving your model is that the next time you want to use this model for prediction, you don't have to do the training again. And so in this case, after I have trained my model, I can load back my model and I can use it to do prediction, and the result is 9. Okay, now, so what I've done here is that I have actually ported this trained model to TensorFlow Lite so that I can actually use this in my mobile application. So let me show you my mobile application. So just one second. There you go. So I am now able to use my mobile device and scribble onto my mobile device to recognize that digit. So for example, I try to write a digit 2 and I try to recognize it, and it tells me that, hey, it has recognized this digit to be 2. If I try one more time, 3, it tells me 3. And then if I write a 0, it is able to recognize that this is 0. Okay, so this is the demo on the mobile application. Now, let's continue with our next demonstration. Now, we want to train a model to recognize fruits. And what I've done here is that I'm using transfer learning to take a model that has already been trained previously, strip off the last few layers, and then add a few layers to the model so that I can actually use this to recognize images. So what are the images I'm trying to train to recognize in this example? So here it is. I am trying to train it to recognize bananas, durians, oranges, as well as strawberry. Okay, so let's take a look. So back in my Python program, so I have a new program. Again, I want to load up import all my modules and libraries, and I want to load up my images. So altogether, there are 54 images belonging to 4 classes, and I want to build my model. So this is what I'm doing. I'm building my model. Okay, and then so let me just run to the part where I can train the model. Okay, so it is starting to train. Now later on I'll show you the link to where you can actually download the source code for this demos, as well as the detailed explanation for others. But for now, let me show you a demo. So as you can see, it's taking a bit of time. Okay, so my training is done. So I am going to save this model, delete it, and I am going to load it back so that I can prove to you that this model can be saved and reloaded so that you don't have to spend time retraining again later on. So what we want to do now is that we want to load from our test folder some images and see how well it can do the prediction. So I'm going to run this. And so here are the results. So here are some of the images that I have in my test folder. So it basically tells me that, okay, for this particular result, this fruit is a banana. Okay, so that looks pretty good. So it's very positive that this is a banana. And then for the next picture, it tells you that this is a durian. Okay, so it's pretty good. The next one is a strawberry. It tells you that this is a strawberry. And the next one is a banana. And the next one is a durian. Okay, so far so good. And this is a banana. And this is a banana. And this is a durian, durian, strawberry, and interestingly, if you have an image of a banana and strawberry, sometimes it can get confused, but in this case, it tells you that, hey, this is a strawberry. Okay, and same goes for the other pictures. And so far, I think it's something interesting. It mistook, for some reason, it mistook this as a strawberry. Okay, so it actually should be a durian. And this is okay, and this is orange is okay, orange is good. Now, this is how you can actually do your image recognition using TensorFlow and Keras and using this technique known as transfer learning. So, okay, the next demo that I want to show you is basically a model that has been pre-trained by Google. So this model allows you to actually feed in an image containing whatever objects you have, a birthday cake or whatever, and it would try to recognize the various objects in that photograph. So let me show you a demo. So I'm going to select a photo from my Photos application. So I can select an image, let's say a cake, and it will tell you that, hey, this is a cake and the confidence is 0.8, so 80% confident that this is a cake. This is pretty good. And the next one, let's say I have a face of a photograph of a human being. So I click this and it says that, hey, it is pretty confident that this is a person. So okay, not too bad. How about this? And interestingly, it tells you that this is a TV. Okay, so this is in fact a computer. So this is pretty fun. So you can actually enter. What about oranges? So it tells you that, hey, this is oranges, and because there are so many oranges that it has detected, so it tells you that, hey, it tells you that the various confidence for each object. And interestingly, I think it saw 5 oranges, but well. Okay, so let me show you a demo of how to actually do image recognition using your webcam. So what I have here is that I have a model that have been trained to recognize fruits like pineapple, strawberry, banana, durian, oranges. So what I have here is that I have run this and my webcam is now activated. I'm trying to put some images on my phone, and hopefully that can recognize my strawberry. There you go, you can recognize my strawberry. And then if I change this to a durian, hopefully that can see this clearly. So okay, so you can recognize this as a durian. And then if I have a banana, so hopefully that can see clearly. I'm not too sure whether you can see clearly, but it's showing that this is a banana. Anyway, okay. So we have come to the end of my talk, and I hope you have a better understanding of deep learning at this moment, and I hope you enjoy the demos. So if you want to learn more details about what I have just talked about, what are the various sample programs that you can try out yourself, please refer to this particular issue of the Code magazine. It's the March and April issue this year. So where I have an article on introduction to deep learning. So basically whatever I have talked about in this talk, you can actually refer to that article to get more details. The code samples are all there. You can actually try it out yourself. So if you need to contact me after this, please feel free to send me an email. I'll be more than happy to answer whatever questions you have. Thank you very much and have a nice conference. Bye-bye.